All right, let's try an airplane. An airplane is flying at 8,000 feet. 8,000 feet, it's flying at 8,000 feet horizontally. Horizontally at 500 feet per second. Yeah, that's fine. 500 feet per second. Away from a man. Away from a man standing 6,000 feet from a tower. Okay, so airplane's flying horizontally away from a man who's standing 6,000 feet away from a tower. Okay. At what rate is the distance between them increasing when the plane is over the tower? At what rate is the distance between them increasing when the plane is over the tower? All right. Good. So let's see what we've got. We've got this airplane. Forgive my not an artist. Let's imagine that's an airplane. It's flying at 8,000 feet horizontally at 500 feet per second. Away from a man, well, there's this tower, and there's a guy over here. He's standing 6,000 feet away from that tower. And the question is, at what rate is the distance between them changing when that plane is directly over the tower? Okay. Now, I guess my instinct would be to call that d for distance, but then we're going to have dt, and that looks a little weird. So let's just choose something else, like let's choose L for length. The distance between them, we'll call it L for length. Okay. So let's see, our given rate. Well, the plane's flying at 500 feet per second, so there's a clear rate there. 500 feet per second. And let's give this a name. Let's say, let's just say X and Y, just to be normal. Okay, so that's horizontal change. So that looks like it's a change in X, dx dt. And if that plane is flying away from him, that distance should be getting greater. So having a positive value makes sense there. Okay. So we were given dx dt is 500 feet per second. And what are we asked to find? We're asked to find how fast or at what rate that distance between them is changing when that plane is directly over the tower. So we're looking for the change in L, dl dt. Again, that's why I didn't call it D, because then it's like DDT, DT, and it looks weird. Okay. So once again, looks like I've got a right triangle situation going on here. So I think x squared plus y squared equal to L squared. Pythagorean theorem, right? Right triangle business. So that's my link between x and L. Pythagorean theorem. Say, okay, well, if this plane is flying away from me, or this person, then x is going to be changing. Okay, so that x is not a constant, but what about this y? Well, it was flying at 8,000 feet, so that's steady. It's staying at the same height, right? So this is actually just a constant. The y height is 8,000 feet squared. Okay. So now I have a clear link between x and L. I don't have to worry about that y. It was just a constant anyway. Sweet. So now I'm going to take the derivative with respect to t. Take my derivative with respect to r, or x, 2x. But then I need to multiply by dx dt. Let's chain rule. Derivative of a constant is 0, so it didn't really bother me what that value was. This derivative is going to go. And I'll have 2L dl dt, chain rule. dl dt. All right. I'm actually trying to find the dl dt, so I'm solving for that. The 2's will become 1. It looks like I have dl dt is, that'll come down, x over L times dx dt. Okay, so I've solved for dl dt. That was what I was asked to find, but now I need to actually evaluate that. So let's look at what we know. The x value is 6,000 feet, so we've got x. Do I have L? No, not yet. Looks like I'll have a little work to do there. But I have dx dt, right? That was one of my given rates. So 500. And let's see if we can figure out what L is. Well, we have it really here, right? We have 6,000 square plus 8,000 square is equal to L square. So L is equal to plus or minus square root of, what, it's 100 million. But of course, we're talking about a distance between the two things, so it's legit to throw away the negative value. And we get L is 10,000. If you recognize a 3, 4, 5 right triangle, you could have saved yourself a little bit of trouble there. But still, we're able to solve for L using Pythagorean theorem. And there we've got 10,000. And that should give us our solution. I have run out of space. dl dt, so the rate at which the distance between them is changing is, this is 30 divided by the 10,000 is 300. And now we got to think. This is a change in the distance, so that's in feet per second. Feet per second. And sanity check, if it's flying away from us, dx dt is positive, then the distance between the man and the plane should also be increasing. So it should be positive. And sure enough, it is. Okay, so that's good too. So there we found the change in the distance between the man and the plane when the plane was directly over the tower. All right, and one more. All right, let's have water drain. Water is draining from a conical funnel from the bottom, right? Straining out the bottom of a funnel at 0.2 cubic inches per second. 0.2 cubic inches per second. Okay. Let's say the height of the funnel is 10 centimeters. 10 centimeters, and the top radius is 4 centimeters. Okay, so that's just talking about the dimensions of the funnel, the shape of that funnel. It's 10 centimeters high, and the radius at the top is 4 centimeters. Okay, at what rate? At what rate is the height of the water changing when the height is 6 inches? We got water draining from a conical funnel at 0.2 cubic inches per second. Got the basic dimensions of the funnel, and they're asking what rate is the height of the water changing when the height of that water is 6 centimeters, or 6 inches, excuse me. All right, so let's see, we're looking for a given rate, a defined rate, and then a link between them. So our given, well, this is inches cubed per second. So we got 0.2 inches cubed per second. That's definitely a rate. It's inches cubed, so that looks like it's a change in volume with respect to time. And now we got to think about it. It's draining out of the funnel, right? So the volume must be decreasing. All right, so there's our given rate. Then let's draw some of our picture. We've got this conical funnel. It's got some water in it. Its height is 10 inches. And the radius at the top, or did I switch? I switched into centimeters, I'm sorry. Inches. There, that's better. I'm consistent. Sorry. Okay, we have 4 inches up top. All right. And that water's in here, so that's at some height h. Some height h, and it has some radius r. Okay. And it's draining out this water, so the height must be changing as the volume is decreasing, but so also must the radius be changing, right? The radius has got to be decreasing as well. But we're given also that the height is 6 inches. They're asking us at that particular place. So let's hang on to that the height is 6 inches. We may need that later. And let's see, to find is the rate of the height, the rate of change of the height of the water. So the rate of change of h, dh, dt. Nice. So I've got my given rate, I've got my to find rate. We're looking at the volume and the height of a cone. So the volume of a cone, this will link the two quantities together. Volume of a cone is 1/3 the cylinder, 1/3 pi r squared h. Again, cylinder, we grab the whole area, pi r squared, and drag it up by h, and the cone is exactly 1/3 of that. All right. Now, I look at this and I go, I think I'm in a little bit of trouble. I really want to link just between V and H. I do have that link, but there's this R squared in here. Now, if I were to just run with it right now, if I were to just take the derivative with respect to t, let's see what happens. This is a product, right? I have a product here, so I have to use the product rule. So I'll have to take the derivative of the first, which would be 2/3 pi r times, so that's the derivative of the first with respect to r, times dr dt, that's my chain rule, times the second, I should have left myself more space, plus, so this was the derivative of the first times the second, plus the first 1/3 pi r squared times the derivative of the second. Well, the derivative with respect to h is just 1, but then I need to multiply by dh dt. Chain rule. All right, and on this side I have dv dt. And so this is what I would get as a result of using the product rule on my volume as it stood here in multipar. And I look at this and I go, okay, well, R, I suppose that's probably findable. I can probably find R. H, well, I was given that, so that's fine. R, I can probably find. dH dt is what I'm actually looking for. So everything is good except for this guy right here, dr dt. And I go, well, this is an additional change that's happening. We have to acknowledge that as the water is draining out and the volume is decreasing, the height is decreasing, so is the radius, right? So there is a dr dt that's validly in there, but I don't know anything about it. Right? This is an additional change, an additional complication that enters into the problem that I don't have a value for. And I mean, we can sit there and try to find out what that dr dt is, but we may or may not be successful, and it's going to be a whole lot of work. So we say, okay, that's what would have happened if I just ran with differentiating the volume as it is right now. Say, well, what I really, really want is just a link between V and H, right? Because I've given dV dt and I want to find dH dt. So if I could somehow eliminate that r out of there, then I'd be golden. Then I can just take my derivative and run. So the key here is to recognize that I have similar triangles, not congruent, similar triangles. This big side is 10, this top radius is 4, the depth of the water or the height of the water is h, and it has some radius r. And I go, ah, there's a key theorem from geometry that corresponding sides in similar triangles are proportional. So I say, okay, as the big side, 10, is to the little side, 4, so is the big side, h, to the little side, r. Corresponding sides of similar triangles are proportional. And what I really wanted was to substitute for r. So I'll just solve for r here. This can simplify. That's 5 over 2. It's h over r. Flip over. R is, this 2 comes upstairs. 2h. 5 goes downstairs. Over 5. Okay, so I just pulled my r up and then multiplied by the reciprocal. Now I have r in terms of h. I can substitute back in and I'm good to go. Let's bring this up a little bit here. Now I've got the volume is 1/3 pi r squared. R now is 2h over 5 squared times h. Sweetness. V is, this will be 4 pi over 5 squared is 25 times 3, 75. H squared times h cubed. Now I'm looking really good. Now I only have a link between v and h. Doing this derivative, I'm going to get what I want. So dv dt is, well, I'm going to do this with respect to h. So 12 pi over 75 h squared, chain rule, times dh dt. Good. So dv dt, do I know that? Oh, I just erased it. It was negative 0.2, right? So I know this side. Do I know h? Yeah, h was 6. I just erased it. Yeah, h is 6, so I know h. And dh dt, that's what I'm trying to find, right? dh dt. So it looks like I've got everything I need now. I'm able to solve. So we're just doing a little algebra now, plug and chug, to find that out. So dv dt was negative 0.2. We have the 12 pi over 75. H is 6, so this is a 36. 6 squared. And dh dt is what I'm actually looking for. Let's see, this is negative 2 over 10, so 1/5, divided by 36 times 12. What's 36 times 12? 432 over 75. Okay, so I just multiplied those two together, right? And then divided it over. And now multiply by the reciprocal, we have negative, the 75 over 5 is 25, no, 15, over 432 pi. Oops, 432 pi. Which is approximately negative 0.011. And now let's think. This is dh dt. dh dt. So that's a change in the height. That should be inches per second. Inches per second. And sanity check. As my volume is decreasing, my height should be decreasing. So the fact that that's negative, that's a good thing. So there we've done it. We found the rate at which the height is changing when the height was 6 inches. Good. So those are related rate types of problems. Given rate, to find rate, link them. Simplify if you need to, get rid of some variables. Take the derivative with respect to t, and then solve for what you're looking for. All right.